All right, good afternoon. So a couple quick things, announcements. On Tuesday, I was messing with my live stream settings for some other event I was trying to host, and it seems like I temporarily messed something up, so Tuesday's lecture was not recorded, so I apologize for that. The notes are posted, however, so you'll be able to catch up with that, or ask your classmates if you needed to kind of better understand what the notes were talking about. So apologize for that inconvenience. Appears to be all working fine now, and I just took a couple extra moments to make sure of that. Okay, today and on Tuesday, we're going to talk about the carbonate system. We've talked about similar topics, and we've been nearly on this topic a lot of times. So what we're going to do with the carbonate system, as you'll see, is kind of pull a lot of pieces together. I'm not really going to dive deeply into how redox is affected by CO2, but CO2 is, like any other species, important with some redox reactions. So whether it's oxygen and CO2, photosynthesis or burning something to mineralize it, there are certainly redox reactions that CO2 is involved with or important as an outcome. So it'll be a little bit related, but a little bit standalone from what we just covered with redox. Now, a few of the core concepts here, we're basically going to use the same acid-base chemistry things that we learned. This will be a diprotic system, so we'll expand it a little bit from kind of what we kept as typically a simple weak acid that we would look at. As you'll see, and as I've posted a MATLAB homework today, we can use computer programs, of course, to deal with this type of system, so just wanted to remind you of that. And I think it'll be a good exercise for you. I'll explain a little more as we go through our lecture today, but I put it due next Friday at midnight. If you guys wanted to have a little extra time on that, given that I didn't give you a whole lot of time between that and the other homework, that does push you into finals week, but just send me an email and let me know if you'd like a little more time to work on it. I hope that it's not going to take too much of your time. I would encourage you to start working on it before next Thursday, hopefully on the sooner side, so that you can tell me on Thursday if you're feeling overwhelmed. Maybe we can spend a little time on where to start, how to get moving on it, okay? So that would be in your best interest and would help me gauge, was this too much? Was this okay? I want to know about that. Okay, today we're going to talk about open versus closed carbonate systems. We'll talk about how the alkalinity conversations goes into that. We've talked in the past with buffering about alkalinity a bit and about this acid neutralization capacity. A lot of that ties into our CO2 system, our carbonate system. So all of that, the titrations plus all of that, and ultimately the amount of CO2, the amount of carbonate in our water will impact many solubility dynamics for different minerals, calcium carbonate, for example. So kind of core concepts here is it's tying a lot together. And so I wanted to try to bring things all together in that manner. Now, I could show you this little link. I think I might as well. I'm not going to spend a lot of time on this, just a little quick excerpt of this video. Nice little demonstration of carbonate system in action and kind of gas exchange. So I'm going to start with a quick review. Just going to play about 20 seconds worth of a video. And by the way, did you guys enjoy the video last time? Was it too long? Felt okay? All right, cool. Felt like you knew a little bit more about redox reactions after that? At least the crazy ones? Okay. Glad to hear that. Okay, so this one I'm just, I was at some point looking for a nice demonstration of soda bottles going boom, and I stumbled upon this particular video, and he takes a heat gun and just sets it up next to the bottle and lets it go. So quite, as you might imagine, what's happening is we've got the dissolved CO2 in the soda, and then it's heating, so the pressure should be increasing because the PV equals nRT, right? So the pressure times the volume is equal to the number of moles of that gas times the gas constant times the temperature. So if the volume's staying the same and you're ramping up the temperature, well, the volume wants to change, so the pressure has to change because the volume is constrained until the volume can suddenly change, right? So, kaboom. Fun stuff there. Kind of similar if you maybe shook a can or whatever. And of course you can do it with this. I like this bottle actually even a little better because you can watch the water level rise. Kind of see the little bit of expansion there now, which is actually kind of interesting. Fluid doesn't usually expand. Kaboom. Okay, so there we go. Now, okay, one more shot. All right. So, Henry's law. How do we know how much of that gas is going to be in the solution versus coming out into the atmosphere? That's what Henry's law does for us, or how much gas will go from the atmosphere into a solution. That's what it's all about. Hopefully you've seen this before, just a little bit of review. And by happenstance, it is another equilibrium reaction, right? So if you have a ton of gas in the atmosphere and a solution that has none of that in it, it will force the gas inside and you'll eventually get an equilibrium between the rates of exchanges, okay? So we describe that with typically Henry's law, although there's also Raoult's law for highly concentrated gases. So sometimes that might be relevant, but typically for kind of our aqueous chemistry, Henry's law is kind of our go-to. So there's a few formulations of it. Pressure equals the Henry's law constant times the concentration in the water is a typical one for dilute systems. Well, Henry's law is for dilute systems, but that's a typical framing of it. But you could also put the pressure of the gas over the concentration in the water, define your Henry's law constant that way, and a few other configurations of how you might set it up, what your units for K, maybe you didn't want pressure units, maybe you wanted concentration units for your gas. So you could do a few different things. This will be our most common one, and I plan on pretty much using it a Henry's law constant that would look something like this, right? Atmospheres per mole per liter, okay? So that would be a typical unit, but I'm just gonna quickly review a few other ways that some people use it. So that's again repeated here, where our Henry's law constant then would be some sort of pressure unit. I was writing atmosphere, you could also use kilopascals. I was writing moles per liter, but they're doing grams per cubic meter. So you can see there's different units we can use. So depending on what Henry's law constant, what those units are, will tell you kind of what units does your pressure need to be in, and so on. You could use it, okay, here's the molar and atmosphere. And some people even go dimensionless or flip it upside down. So I guess that's the one I have first. So if you flip it, you could have it such that you're doing concentration in the water compared to the concentration in the air. So sort of inverted Henry's law constant. Okay, sometimes maybe that's more convenient. And finally, sometimes you'll take the concentration units of the same type. So you could do grams per cubic meter of CO2 in the atmosphere versus grams per cubic meter of CO2 in the water, right? And then that turns out to be a unitless constant. And in that case, you would know if that number is greater than 1, then the chemical prefers to be more so in the numerator, right? It's over 1. So if you go all the way there to the unitless, maybe that's a little more convenient to compare to the 1. But primarily, we can expect to be pretty much using something like this, maybe this. We're not even going to have time to do a whole lot of any of it. So just for our CO2 sake, now you know, now you remember what the Henry's law constant is about. Okay, and I'll put that on the formula sheet for the final. Okay, Henry's law coefficients depend on a couple things. One is temperature, and another is other things that are dissolved. So it turns out that if you want to know whether or not a stream or a river will be good for supporting some fish like trout, they like a lot of oxygen. You might have, if you know anything about fish or fishing, you might know that trout tend to like cold water. Well, it's probably more so that they like oxygen-rich water. And the cold temperature allows that to happen much better. So if we take a look, if we are in the range for these constants closer to 0 Celsius, so closer to freezing, compared to closer to Louisiana, we can see that this constant goes from, I don't know, 2.5 to 3 to more like 5-ish. Okay, so that's a pretty big change. We can imagine that that ratio will have a big impact on how much oxygen is in the water. Yeah.
So this is like specifically describing that at higher temperatures, oxygen gas likes to be a gas as opposed to being dissolved in solution.
Exactly. So at higher temperatures, the equilibrium is such that there's more of it in the atmosphere compared to the water.
Okay.
Yeah.
Okay.
Yeah, and you'll see that this, I guess this constant is in per, this is atmospheres, I guess. Okay. Which doesn't make sense to me, but we'll pretend that it does. Okay. In fact, if you were to take a look, I think at our highest amount for oxygen can be something like, if I recall correctly, 16 milligrams per liter near the freezing point, and typically at around room temperature, it's more like 8 to 10 milligrams per liter at about 25 Celsius. So you can see it's a pretty big difference. There are some co-solutes that would affect things. So, for example, the amount of chloride does tend to inhibit oxygen from dissolving a little bit. You could imagine perhaps something could encourage it, but you could also have some things that just say, well, because of the presence there, some of the things we talked about early on, it just is less likely for oxygen to be there. So you do have a few things to consider there. Ocean water will be a little different than fresh water. Okay, so let's do a quick practice problem, make sure this is all piecing together nicely. So we have a CO2 example. So the concentration of carbon dioxide in water at 20 degrees Celsius is determined to be 1.00 times 10 to the minus fifth moles per liter. The Henry's law constant for carbon dioxide under these conditions is 3.91 times 10 to the minus 2 moles per liter per atmosphere. And remember to check on what those units are telling us in terms of how our Henry's law constant is set up. So the question is, what is the partial pressure of CO2 in the air? We'll call that partial pressure as P CO2 is the question, and the units should be atmospheres. And remember, our simple formulation would be something like the pressure is going to be equal to the Henry's law constant times concentration in the water. Okay, so you've probably gotten your calculators out, started punching this in. Have you checked the units yet about what's going to happen with them if we multiply them like I'm suggesting? Something weird's happening, right? Right. So we're either getting, so if we take the K, which was given as moles per liter per atmosphere, and if we multiply moles per liter per atmosphere times moles per liter, we're getting moles squared per liter squared per atmosphere, right? So clearly my simple formulation, I was just reminding you, like, this is the kind of a standard format. Well, we just encountered the error, right? Apparently they were giving us one of these that was inverted. So all we have to do here to remember the Henry's law constant is remember that these three things are related, something like this, and then check, are the units working? Nope. Oh, okay, let's flip that h. 1 over h is what we need. Then the units work out, and this should be fine. So, and I hope that's what the book will explain in a moment. So if we do 1 over 3.91 times 10 to the minus 2, multiply that by our 1.00. And by the way, I was thinking to myself that 10 to the minus 7th was going to be a pretty small number for CO2. So we had, so this would be 1 atmosphere per 3.91 times 10 to the minus 2 moles per liter. These should then cancel. Anybody have this number for me?
2.5 times 10 to the minus 4, or 2.57.
Okay, so 2.56. Okay. Now, anybody remember kind of approximately what's our CO2 in the atmosphere in parts per million? Nobody? 0.5? No, not 0.5. Okay. Well, good thing we're talking about carbonate today. So it's around 420, 425-ish right now, parts per million. So if you think about the atmosphere composition, as we talked about in the past, ppm is kind of like a percentage, but instead of per 100, it's per million, right? So 425 per million. It would be like, we could transfer that into a percentage and it would be 0.000 or whatever. So that's what I'm actually going to point out here is if we take 0.000256, if I have that right, 1, 2, 3, yep, 256 as a fraction, so we could move that over to 2 spots. Let's see. Out of 1 atmosphere, which is what we kind of have at standard conditions, we have that much CO2 in this scenario. So that translates to 256 parts per million. So just checking on that in my mind, I'm thinking to myself, okay, we are reasonably close to, maybe this is pre-industrial, or maybe this is just a slightly different, like a closed bottle and something was changed so that it's not quite normal atmosphere, but something different. Okay, so let's just double check. The book says, I don't even remember which book I took this from. So we have this K, and yeah, they did take it as the K that is the C star, the concentration in the water divided by air. And so we set it up in that way and divided by that K instead of multiplied by it. Okay, so then we get 256, 2.56 times 10 to the minus 4th atmospheres. Okay, does that make sense? Any issues? So Henry's law is pretty simple. It's just the units can be a little weird. So you just have to pay attention to the units and the relationship will kind of set itself up, okay? So we could solve, of course, if we had the pressure and the concentration, but we didn't know the Henry's law, but we knew it was at equilibrium, we could then find the Henry's law. And so we could do a lot of stuff like that to solve for any piece we needed. Okay, so a few general notes about the carbonate system. So the Earth's atmosphere currently contains, I looked it up, I think today's value is something like 427 ppm of CO2 in the atmosphere. That corresponds to something like 0.00427% of the atmosphere. So we have a large percent is nitrogen, it's about 78%, about 22-ish% is oxygen, and some trace of a lot of other things, including CO2. If we look back in the historic range, from different ways we can check, lots of million years ago, it's been all the way up to 1600 and all the way down to around 200. In our aqueous systems, we describe CO2 dissolving as CO2 in equilibrium with CO2, like the gas, in equilibrium with aqueous. And then the aqueous reacts with water, has another equilibrium constant to form H2CO3, which is our carbonic acid. We've talked about that before, and that's the basis of our diprotic carbonic acid, right? Which then dissociates to bicarbonate, which is HCO3 minus, and carbonate, which is CO3 2 minus, which we'll talk more about. So just wanted to give you a little context there. And of course, when we drink carbonated beverages, we're adding that carbonate to spice it up some, make it more interesting and whatnot. And if you had something fermented, you're getting a lot of CO2 from the fermentation process and adding that carbonate in that way. Okay, so these equilibria, if we want to be fancy about it, we could plot it all out to say, all right, we have CO2 in the atmosphere up here. Then it's going to be in some equilibrium equation defined by our Henry's law, constant, and it will exchange then with whatever solution of water we have, assuming that it's open to the atmosphere, right? It would be different if I filled this completely and closed it and sealed it off, because then maybe I do some reaction that removes it, or maybe I removed it beforehand, and there's no exchange, right? It's a closed system. But with this open system, we have, of course, an equilibrium with the Henry's law constant. We technically have an equilibrium with this reaction here, CO2 reacting with water, to form H2CO3. However, these two we're going to treat the same and just call it all H2CO3 star. Because as soon as we have any of it dissolved, functionally it's going to be available as H2CO3. Even though there's an equilibrium there, we're just going to treat it all the same, because functionally it's going to act the same. We've got it into the water, and that's what kind of matters, all right? So that's why, so far, if we've ever talked about it, we've seen the little star. It's just meaning it's also including this CO2 dissolved that's technically not reacted with water yet, but it will. Okay, from there, we have our, if you remember, our alpha fractions, right? Alpha 0 would describe how much is in this form. So we will describe, see it? The alpha 0 will relate to this, then alpha 1 will relate to the next equilibrium, the HCO3 minus, that's our bicarbonate. And then we have that in equilibrium with carbonate, CO3 2 minus. Okay, so we have carbonic acid, bicarbonate, and carbonate. And alpha 2 would describe how much is in the carbonate form compared to total. Okay, of course, if we had something that, some mineral that might precipitate, we'd have like calcium, then we'd have something additional to consider in another, another reaction. So that's typical in many systems, ocean or in fresh waters, calcium is fairly abundant. So that's often something that can contribute carbonate to a system or take it away. All right, so that's kind of the gist of it. We have basically a diprotic acid. We've done a lot with acids, so just making it diprotic doesn't complicate it too much. I know we didn't delve into it too much, so that'll be a chance to do so today and next time. But overall, it's pretty straightforward, almost the same thing as what we've done so far, except here we may have that equilibrium with the atmosphere if it's an open system. That's going to be our biggest difference.
Sorry.
Yeah.
And so for that last one, is that making equilibrium with calcium ions?
So yeah, so this last one here was not what I was intending to focus on, but this would be in equilibrium with calcium if calcium is present. And this would tie it into, it's not just calcium, there's magnesium and other things that could also react. So this is just a little side note. Most of what I was meaning to explain here is the standard ones we find. And the side note is calcium, if it's present, it may also be important. But overall, this would kind of be our typical equilibrium, just looking at the carbonic acid system, with atmosphere. So if we had pure rainwater, for example, what's the pH of natural rainwater? Well, it's not 7. You might think it's 7 because there's kind of nothing in it, but there's going to be an equilibrium of CO2. And as you've learned, when we add some acid to water, even a weak acid, we'll shift the pH a bit and give it some buffering capacity. Yeah, it's the pH of natural water is somewhere around 5.3, I think. Of course, that'll depend on how much CO2 we have. Okay. So I mentioned the alpha fractions. Here I have them all written out for you for each of our equilibrium reactions. So we have for the carbonic acid, H2CO3 in equilibrium with bicarbonate. That's our first Ka. So we've done a lot with just one single Ka. In a diproduct system, we'll have two equilibrium reactions going on. So we'll have Ka1 and its products over reactants, right? So this is going to be the products of this reaction, H plus and HCO3 minus on top, divided by our H2CO3. That is neither a liquid nor a solid, the H2CO3, so that is still there. It's not excluded or placed to 1. And we have a value. That is 10 to the minus 6.35. Okay, so then we have an equilibrium between our carbonic acid and bicarbonate. And now next up we'll have between bicarbonate and carbonate right here. And so this one is 10 to the minus 10.33. So already you should have in your mind that we could make a graph of this stuff, right? And if we made a graph of it, we need 3 different species. Let's say graph it versus pH, okay? PCPH. By the way, this is basically what I'm asking you to do on the MATLAB homework. We'll have some species dominating at highly acidic, and same deal, that'll dominate our total at highly basic. And then we have to think about, okay, at what pH, and we'll go ahead and just put this at 7. I'll put a 10 mark, and I don't know, a 3 mark, something like that. So at what pH do we have 2 crossing? Well, the first 2 are going to cross at 6.35, so that'll be somewhere around here. And then the next one crosses at 10.33, so that'll be somewhere around here. And the first one should be the most protonated one. So the most acidic should be H2CO3. It's going to be this guy, and eventually it's going to do that. That'll be in equilibrium with HCO3 minus, because that's the next most protonated one, which will cross right there, come up and dominate for a little bit, and then it'll go down like that. Okay, and then the last part would be CO3 2 minus. So hopefully this is looking pretty familiar, even though now we are adding a 3rd line, and previously we've always only done kind of 2 lines. Hopefully all that looked pretty much like we've done it before, right? Yeah, got a question?
So, and I'm assuming that we're finding the pH in like the same conventional ways that we always have.
There will be, yeah, there may be a couple differences, especially when we make it an open system, but we're gonna walk through that. But yeah, you were all of the same principles that we've learned about finding the pH or finding the speciation for these given a pH or something like that, they all still hold true. So the fundamental chemistry is the same. Okay, so with all of that, and with it in mind that maybe we want to find the speciation or get things in terms of pH, if we write out each of the alpha fractions are actually very similar to what we've done, but now we have 3 species instead of 2. Okay, so they do get a little bit more complicated. So alpha 0 is the portion that is carbonic acid divided by the portion that is total, right? That's, by definition, that's kind of plainly obvious, I hope. That means it's H2CO3 plus the concentration of HCO3 minus plus the concentration of CO3 2 minus. And each of these alpha fractions are designated accordingly. Now, in the past, one thing we've done with the alpha fractions is we've derived these as a function of pH and the K values. So we can do that here. I'm going to skip the derivation for all of our sakes, but we could derive it. It's algebra, right? We could say, okay, well, we can substitute given our equations up here, we could make substitutions until we have everything in terms of H plus and the K values. Okay, for each of these we can do that. And I think on my next slide, or a slide soon, we will have all those kind of plotted out and derived. Okay, so not yet, but I'll have those, and you'll be able to see, you know, we can rewrite this in terms of Ka1 times Ka2 divided by H plus squared, blah, 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 whatever the derivation becomes. Okay, so if we plot this for a closed system, some known amount of CO2 dissolved, and we can actually take a look and see that that looks to be 10 to the minus third moles per liter, because this is a PC plot. So that should be 10 to the minus 3 is about right there. And sure enough, that's what it's talking about. So for a closed system, it looks very, very much like all the other acid-base equilibrium diagrams that we've drawn. So now we're doing diprotic. Like I said, it's just a small change. The only other small change you'll note is once you get into the territory, after you pass kind of the second equilibrium point, your slope goes from a slope of 1 here to now 2 here. So the slope increases a bit because now you have 2 different species that are important there. Where you have practically no CO3 2 minus, this is staying at a 1 slope. So don't worry too much about that. Just a tiny side note, I'm not going to ask you to do probably anything with that. But we did talk about that slope being important previously and how we could use it. So just pointing that out. Okay, so you've seen this essentially. We haven't added or done too much with the diprotic, but you've had some of that. Okay, we've also talked a little bit about alkalinity, and I want to come back to these definitions of alkalinity and of this ANC, which is acid neutralization capacity. Because they relate directly to the carbonate system. So for the definition of alkalinity, we said this is the sum of titratable bases that we can titrate with a strong acid to defined endpoints based on the carbonate system. So when we did all those titrations and everything, what we said was we can do an electroneutrality balance. And then if we take all of the things that relate to how much protons are in water on one side and move everything else onto the other side, we've essentially segregated it, still balanced, I mean, we're still with an equality between them. And we can say that we can get the sum of the non-participating cations and anions on one side and all of the species that are participating on the other side. So I'm just going to go back through this chemical definition with you. So acid neutralization capacity, we say, is equal to HCO3 minus plus 2 times the carbonate, CO3 2 minus, plus OH minus, and then plus the sum of any other titratable bases, so basically weak acids. We talked about the generic HA with an A minus or the HB with a B minus, right? So that's what this is talking about. In this case, we're talking about a base minus the H plus concentration. And we could get the same exact equation set equal to the sum of the non-pH related cations minus anions. Okay, so we had that equation that we talked about. I'll continue reading here. So we say B minus represents any other titratable bases. In natural waters, that could include borate, seawater, maybe there's phosphate, silicate, humic substances. I guess borate is maybe more important for seawater. Ionic forms of humic acids, fulvic acids, which is basically like the organic matter from soils and decaying leaf matter and stuff. The other way we can derive this, which is I was getting ahead of myself, is that kind of the geochemical or charge balance definition, where this would be the sum of the BC minus the sum of SA, which are these non-pH active cations, and so strong bases and strong acid cations and anions. So the sum of things like sodium, potassium, calcium, magnesium, minus the sum of things like chloride, sulfate, and some others. Okay. So let me just write this. Okay. So we have kind of two definitions of the acid neutralization capacity, and we also say this is the same thing as alkalinity. So if we have a simple system with just CO2 in it, and then we think to ourselves, how much strong acid or base do we need to add to shift the pH? This becomes quite simple, because if there are no other things in here, so if we get rid of this for a moment, and I'll erase this in a second. So if we got rid of that, and we wanted to change the pH of our system, well, we know exactly how much alkalinity we have based on this equation. So if we needed to change the alkalinity some amount or adjust the pH, which is over there on the corner, right? If we wanted to adjust that, well, we know that it's going to relate directly to that net strong base term, right? That strong acid or strong base that we could add to get there. So it actually turns out to be quite convenient that this relationship exists and that we can work with it. Of course, if we had something else, we might also have to consider the other piece in there, but we could definitely do that as well. Okay, so I say all that to say that it will simplify as we go. Okay, so just a quick little reminder about this alkalinity and ANC. So the way we're describing this acid neutralization capacity, how many units of H plus can be neutralized by CO3 2 minus? Got 2. Everybody else agree? Anything else? So the question is, how many H pluses can CO3 2 minus neutralize when we're talking about adding an acid? Yeah. Exactly. It is 2. And therefore, HCO3 minus should be able to consume or take care of 1. Right. So that's why in our equation we have the 2 out in front of the CO3 2 minus. This is coming back to our proton balance type of an approach that we talked about. And it shows up there for that reason. Okay, so for the carbonate system just by itself, like I said, we get rid of that any other bases, if they're not present, our alkalinity equation is always this. We have HCO3 minus plus 2 times CO3 2 minus plus however much OH minus is in the system, which of course we can put into the framework of H plus, that minus H plus. And by the way, we can put each of these in the framework of H plus, right? We could find each of those terms as a function of H plus and as a function of the amount of CO2 that there is there, and the alpha fractions accordingly. Okay, another thing we could write, we could say that our base neutralization capacity, it's a little odd or different, we could write it in a similar manner but in reverse. Now, I don't think we really need to focus too much on that, but it's basically the same principle, except if we did the OH minus balance instead of the H plus balance. So then H2CO3 is essentially accounting for 2 OH minuses, HCO3 is accounting for 1, and H plus will account for 1, and all that minus OH minus. So don't worry too much about that. It's just if we put it all in reverse, we can have the same principle. Got a question?
Yes. So the A and C, the acid neutralization capacity, is that essentially the electron neutrality equation, but moving the hydrogen all the way to the right?
Yeah, so we get to the A and C if we start with the, I think it comes directly from the electron neutrality equation. Yeah. And so what we could say is we can start with the electron neutrality equation and just rearrange, right? So if we had a solution of pure water, we start with H plus on the left and OH minus on the right. Yep, with no CO2. Right, so then we could put 0 equals OH minus minus H plus. Okay, and in a pure water system, of course, that makes sense. We're at pH 7. Both of these are 10 to the minus 7 moles per liter. It equals 0. As soon as you add something else, now we can have some sort of acid neutralization capacity. Right? As soon as we add a little CO2, you have all these other species in there. They will contribute, and they may even shift around these guys a little bit too.
Yeah, because didn't we learn earlier that like the left-hand side minus the right-hand side is defined as the alkalinity, and right? Or
we often solved for pH that way, to do a left-hand side minus right-hand side. Start with the electron neutrality, find the root to say, okay, left hand minus right hand equals 0, solve for that in that manner. But we did derive the alkalinity in a similar manner by separating the strong base cations and the strong acid anions to one side and all the other species on the right side. Okay. All right. So, and this is just a repeat of what I just said there. We can do the strong base cations minus the strong acid anions over there. So, quick example problem. What is the alkalinity of a solution containing 2 times 10 to the minus third moles per liter of NaHCO3, 3 times 10 to the minus third moles per liter of lime, calcium hydroxide, OH2, 1 times 10 to the minus third moles per liter of potassium hydroxide, KOH, 1 times 10 to the minus third moles per liter of sulfuric acid, and 6 times 10 to the minus third moles per liter of hydrochloric acid, HCl. So take a moment and see if you can find the shortcut that can make that a little quicker than it feels like. Okay? Give that about 2 or 3 minutes. So how many of you, maybe show of hands, started working on figuring out these guys? Okay, and how many of you started thinking about these guys? Okay, so some of you thought about everything. Okay, and some of you just weren't thinking about it. All right.
Do you use like the concepts of like the strong acids and strong bases like dissociating entirely to like make some assumptions and then
Yeah, so the reason we have the strong acids and strong bases set aside here is because they dissociate entirely and they don't have any impact on or any interaction. They're not taking away any protons or OH minuses as you shift pH. They completely let go of it, and so they have no impact, regardless of the pH within water. They have no impact on the current amount of H plus or OH minus. So when we set up and segregate these, that's why we get net strong base on one side, and we get stuff that's the buffering capacity stuff on the other side. So yes, exactly. And the shortcut here would be to take a look and realize, I guess I didn't say this, but we're going to assume this is a closed system. So no other source of CO2. What we can find is we should be able to identify that we have sodium and a known amount. We have calcium. We need to do 2 times the concentration because it has 2 charges, and we're essentially doing a charge balance here. And if you notice, for every 1 calcium, we're releasing 2 units of base, OH minus, right? So that makes sense as well. We also have potassium. We also have some acids, so we're going to have 2 times sulfate, so 2 minus, and chloride. So if we sum up these guys, that should be our acid neutralization capacity. So that if I take a glance at these, they are all something times 10 to the minus third. So I'm just going to ignore that for a second and say we have 2 sodiums, we have 3 calciums times 2, so that's 2 plus 6, that should give us 8. Another one is potassium, so we're at 9. And then we have some sulfate and chloride to deal with, and we have 1 sulfate, but it's times 2, so that's going to be 2, and then 6 of our chlorides, so that should be 7. So 9 minus 7 should be 2 times 10 to the minus third moles per liter of acid neutralization capacity, I think. That kind of makes some sense?
you're multiplying the calcium hydroxide concentration by 2 for the Ca2 plus to get the concentration for Ca2 plus. Multiplying the
Yeah.
Okay. And then you have the same for sulfuric acid.
Yep. So we'll check to make sure this is correct with the book's solution here. Okay, so except for the carbonate that was released, everything else is a strong acid or base, so we can separate it as we talked about. And we should be able to rearrange this to sodium plus 2 calciums plus potassium minus 2 sulfates. In the book as a typo, it should have been either minus this plus this or minus minus. So corrected that here, minus chloride equals all this stuff. And we can just focus on this side of it, right? So that turns out to be, maybe I did the math wrong in my head. We'll trust the book even though they made a typo, or maybe, I don't know, maybe we shouldn't trust it. Maybe that's the difference. They got 1 times 10 to the minus third moles per liter. I was thinking it was 2, but they didn't catch. Yeah, I think they did something wrong. So I don't know. It's either 1 or 2. But you get the picture of this process, right? I'm not going to spend the moment the minute or two to double check all the algebra right there, but the process was correct, right? We do a charge balance, and we do the sum of the cations minus the sum of the anions, and that is our acid neutralization capacity. Now, these are the cations and anions that are not dealing with anything relating to pH, right? These are the strong acids and strong base cations and anions. Okay, does that make sense? Okay, so till now, we've really been dealing with closed systems where CT is constant. I did introduce the concept of the open system, but here's one more graph. Here's what it'll look like for the closed system. And by the way, part of your MATLAB homework is to essentially recreate this. Maybe I gave you a different number for the CT, but it's something not far from here if I did. So as you work on that, you can kind of use this as a guide to say, okay, I want something that looks a lot like that. And if it's not looking a lot like that, maybe I did something wrong. Okay, so you should be able to get at that. And again, we will get there by defining each term, like H2CO3, as a function of the total concentration times that alpha fraction, which will allow us to make it pH dependent. Okay, we'll get the known constants plus the pH, and then we'll be able to graph it accordingly. And it will take care of the slopes for you automatically that way, because that'll be built into the equation for each of these pieces. Okay, so you don't have to think too hard about it. Let MATLAB do it. You just have to get the right pieces into place so that for each line you have y equals essentially x, well, a function of pH, right? M, some slope times pH, and no plus b, it'll, you just need this as a function, right? That'll handle it. Okay, so let's get there then. Let's develop these alpha fractions and start talking about the open system. I think we can do, I think I've got both at the same time kind of here. So, yeah, the current CO2 concentration in the atmosphere is about 427 parts per million. Tends to rise about 1.5 parts per million every year. So what people are concerned about with CO2 emissions. So essentially, Henry's law then dictates that equilibrium like we talked about. I think we saw a different Henry's law constant earlier. Here we have 10 to the minus 1.47 for a scenario where we have moles per liter per atmosphere at 25 Celsius. And of course, we can have these different equations. Now, our alpha equations are going to be the same whether or not it's open. But for an open system, we can then include the CO2 into the calculations directly because we have this term H2CO3 as a function of the partial pressure of CO2 in the atmosphere. Okay, so we could calculate this for a soda bottle that has a lot of CO2 pressure in its atmosphere, or we could calculate it for just open to the regular air. So alpha 0 times CT is our equation for carbonic acid. We could also set that equal to then this Henry's law constant times the partial pressure of CO2. Okay, so we can include the pressure there directly, and then that correspondingly would affect any of our other alpha fraction calculations. Okay, so what does it look like when we plot our system? And this is the second task on your MATLAB homework, so hopefully you're able to get something that looks a lot like this guy. And by the way, if I thought I had slides that showed exactly the alpha fraction derivations as a function of pH and the K values. If I don't have that in here, it'll definitely be in the next slide set. I'll make sure you have that. Might even be something I'll just go ahead and give you on the formula sheet as well. I don't know if I'm really going to have you do that much plotting and stuff on the exam, but I'll make sure you have this. Okay, so when we think about the open system, what's going to happen is at a very acidic condition, we're basically going to have some, our amount of CO2 will be dominated based on that equilibrium with the Henry's law. Okay, we will have as much CO2 into the water that will dissolve, and all the CO2 in the water will be in that form. Right, so all of our total carbonate concentration is all going to be in H2CO3 form. Right, because the others are just so small. The others are very small fractions going basically to zero. Okay, very negligible. So when we plot our C total, it's going to start here. That's our equilibrium point with atmosphere. Now, what's interesting is as soon as we start shifting higher into pH, and as soon as we start getting some other forms of carbonate, well, more CO2 from the atmosphere comes back into the water. We're going to assume the atmosphere has a constant amount. We're not going to deplete the atmosphere of CO2. Now, maybe globally the oceans could make a difference over time, but in my bottle that's open to the atmosphere, we're not changing the amount of CO2 in the atmosphere. So there's always going to be the same amount of H2CO3 in here from that equilibrium. So rather than H2CO3 kind of dying off, we continuously have input from the atmosphere. So instead of drawing it that way, this H2CO3 line is actually going to go straight across because it's always at equilibrium. There's always going to be that much available to come into the water. Okay? So that means as soon as we go more and more basic, we have more total CO2 if we include the bicarbonate and the carbonate, because our carbonic acid stayed standard across the whole pH range because more was just going to add from the atmosphere. And suddenly, as we start adding some HCO3 minus, we have more total carbonate. Okay, so that's the difference when we have an open system, is our total carbonate can increase further and further. We're not limited by some cap. So we can find values for CO3 minus and for CO3 2 minus accordingly. Now, in each of these cases, it kind of goes back to the same situation where we can say alpha 0 times CT is equal to that Henry's law constant times the partial pressure. Well, we can also say alpha 1 is some function of C total. Well, let me rewrite that. We'll say alpha 1 times C total is the bicarbonate. And so if C total changes and increases if we change the pH eventually, with increasing pH, well, our carbonate can continue to change as well. Excuse me, a bicarbonate and our carbonate. If I can speak. So what we see then is kind of each of these components can be related back to our calculation of how much H2CO3 is present. Okay, so it does complicate the system a little bit, and that's what this factor analysis is discussing up here on the left. In a closed system, we basically have three variables. We could look at the pH, the current total, the sum total of our carbonic acid, and essentially our acid neutralization capacity. Those would be the three pieces we could look at to characterize the whole system. Well, with an open system, there are four variables, so we have to include the Henry's law stuff. Complicates things a little bit, but we should still be able to get defined well-defined plots to make and relationships between each of these. Okay, so this is another graph to look at. Now, I did not ask you to plot the H plus or OH minus in the MATLAB homework, so you can clean it up a little bit in that sense. And I think all I asked for was the 3 here and the C total for this guy. For the other system, I just asked for the 3 and don't worry about the C total. So 4 plots, and the last one is just adding each of the others together. Should be something that you can do in MATLAB. Like I said, if we didn't have the tools in place in the next couple of slides, I'll make sure you have them next time to really see exactly how to get HCO3 minus as a function of pH. Okay, so that's something that you'll need to code into your program. Okay, one other thing I wanted to note: the caption for this particular figure. This is for a partial pressure of 10 to the minus 3.4 atmospheres. Now it notes that to increase your pH with a net strong acid, or excuse me, a net strong base, should be added, must be added. To decrease a net strong acid, you have to add, and that change, as soon as you add exactly some amount of net strong base or net strong acid, you've changed the alkalinity by exactly that amount, right? Because you've shifted this. So just keep that in mind. If we have just a pure carbonate system, as soon as you add the net strong base or acid, that's how much you've changed your alkalinity. I guess that's always true. Okay, here we go. This is what I was hoping I had up here. So for the different terms, in order to write alkalinity in the form of these pieces, and I guess maybe for the plots we would also need H2CO3. But let's take a look at the HCO3 minus and the CO3 minus. We can see that if we take our bicarbonate and define it as in equilibrium with HCO3 over H plus, so we basically take our Ka1, which says it's products over reactants. We rearrange to put it in to solve for HCO3 minus. We get HCO3 minus equals Ka times H2CO3 divided by H plus. From there, we could substitute in, and instead of write HCO3 minus, we could put in the Henry's law, right? The Kh times the pressure. Then we can do the same thing using that equation that we just derived in equilibrium with CO3 minus, rearrange to solve for CO3 minus, and substitute in, and essentially we add the A2 times the A1 times the K times the CO2, and now we have an H plus squared on the bottom. So let me make sure that was clear. So we start with Ka1. This is the first equilibrium constant. This has the products, H plus and HCO3 minus for our first equilibrium in the carbonate system. This is describing our equilibrium between carbonic acid and bicarbonate. Right? So we're describing it there, and we rearrange to solve for HCO3 minus. And we can do that simply by dividing both sides by H plus and multiplying both sides by the H2CO3. So we'll get Ka1 times H2CO3 star divided by H plus. That's where we got this part. Okay? So from there, we can insert, instead of H2CO3, we put in the Henry's law. It comes in there and tells us how much we have. Okay, so now we have it in terms of partial pressure, constants, and H plus. Okay, so that's very handy. And now with those two, we can essentially plot two of our lines. Now, so these two will be the two of the plots. It turns out that the one we were missing here, H2CO3 star, anybody want to tell me why that one's obvious? Have you seen it? I only just noticed myself, so no harm in not noticing this. But this one's very simple as a function of pH, and I talked about it earlier, and it's because it's an open system. So what should it be? No, in fact, just look right here. What did we substitute for H2CO3? Yeah, the Henry's law told us we have some amount. And no matter what pH we're at, we just get back to equilibrium with the atmosphere, right? So we always have the same amount. So that's why in my mind I was like, oh, duh. So this should just be exactly that, the KH times the partial pressure of CO2 at all pHs. So that's a very simple line. So now we have, for the MATLAB plot, we have 1, 2, 3, and the fourth one we add them all together and plot that. Okay? So that should be something you could do. Another thing we can do is substitute all that into the alkalinity equation. And this time the slightly more complicated side, right, the kind that is pH dependent. And now we have a pH dependent function for our alkalinity. And so we can get that alkalinity equation in terms of only constants, pH, and the partial pressure of CO2. Okay? So now we can describe the entire carbonate system and solve lots of problems with it. Okay. So make some sense? Do you feel today like, wow, some of these pieces are coming together? I actually learned something earlier. So neat to kind of see some of these pieces come together. All right, that's all I've got today. So see you on Tuesday.